Hey, if you are new here, this is Chandan and you are watching the Learning Field. So this is our lecture what 9 of linear programming problem. Okay, so in the 8th lecture we discuss the dual problem. Okay, that is the duality in linear programming, and in this lecture, that is in lecture 9, we continue the duality of linear programming. Okay, so duality of linear programming is a very important concept, and based on duality there is questions comes in GATE, obviously. Okay, GATE exam. There are various types of theorems and examples, and the applications of theorems are in the duality. Okay, so read the duality very carefully. Okay, so this is the very important chapter for GATE exam. Okay, and this is also helpful for CSIR NET and the SLST exam, and in also for SET exam. Okay, so and before starting, I am requesting those who are new, those who are watching me first, then please do like, comment and share, the subscribe the channel. Okay, so the theorem first we read is weak duality theorem. Okay, if x bar transpose, that is this is vector. Okay, so if x vector equal to x1 x2 xn is the feasible solution to the primal LPP, that is make max of z equal to maximize z equal to C transpose x subject to Ax equal to b. Okay, so these are the summation notation of the C transpose x and Ax equal to b. Okay, so this is the primal problem, and u equal to u1 u2 and um is the feasible solution of the dual LPP with dual LPP, which is the dual LPP, this one. Okay, so minimum of w equal to B transpose u subject to A transpose u greater equal to C. The dual is the from we get from the primal problem. Okay, then C transpose X equal to summation Cj xj, this is less equal to Bi u, I equal to attempt. That is what, that is the case is C transpose X is less equal to B transpose u. That means what? That means this is the objective function, value of the objective function in the primal problem, and this is the value of the objective function of dual problem. That is what? The value of the objective function in primal problem is less equal to the value of the objective function in the dual problem. Okay, this is the weak duality theorem. In general, we know that the objective function in both the cases, that is in primal problem or in dual problem, are same. Okay, this is a theorem also, which is the fundamental theorem of duality, you can say, and this is called the weak duality theorem. Okay, now let us come to another theorem, which is unboundedness property. Okay, if the primal or dual problem has unbounded solution, then the dual or primal problem has no feasible solution. That is, first read it. If the primal problem has unbounded solution, then the dual problem has no feasible solution, and if the dual problem has unbounded solution, then the primal problem has no feasible solution. You can read these types of theorem by this. Okay, when you spelling this primal, then you spell this one. Okay, and when you read this dual, then the bracket term. Okay, so this is the rules to study these types of theorem. Okay, now let us come to another important theorem, which is the fundamental theorem of duality. Okay, if the primal or dual, if the primal problem has finite optimal solution, then so does the dual. That means the dual problem has also the finite optimal solution. Also, the optimal values of the objective functions are same in both the cases. So this is the fundamental theorem of duality, and this is also you can vice versa case maybe occur. That means if the dual problem has finite optimal solution, then also the primal and also the primal optimal values of the objective functions in the both the cases are same. Okay, this is the fundamental duality theorem, and we just say that C transpose X, that is the objective function, is the value of the objective function is less equal to B transpose u. This is the weak duality theorem. Okay, this one. Now let us come to another theorem, which is existence of bounded optimal solution. Okay, existence of bounded optimal solution says that a linear programming problem has a bounded optimal solution if and only if there exists a feasible solution of both the primal and dual LPP. Okay, so this is the existence of bounded solution. That means in cases the both linear programming has bounded optimal solution if and only there exists both the feasible solution for the both primal and dual LPP. Okay, so this is a clear cut theorem. And the next theorem is the non-existence of bounded optimal solution. Okay, so if the primal LPP has feasible solution but the dual has no feasible solution, then the primal has no unbounded solution. Okay, non-existence of bounded solution, this is the theorem. And the next theorem is, if the primal LPP has no bounded solution, then the dual has either no feasible solution or unbounded solution, and this is also for the unbounded case also this theorem holds. Okay, and in this case there is also these terms may be happen. Okay, now these are the 4 most important theorems of duality. Now let us comes to the summarization of these 4 types of theorem. Okay, so this is the summarization. So see, in the table, this is the primal table, the primal LPP, this is case of dual LPP, and this is the conclusion. Okay, so read it. So if the primal LPP has feasible solution, then the dual LPP has feasible solution, then conclusion is both the LPP has finite optimal solution. If the primal has feasible solution, dual has no feasible solution, then the primal LPP has unbounded solution. Okay, next one is no feasible solution, primal has no feasible solution, dual has feasible solution, therefore dual LPP has unbounded solution. The next case is, if the primal has no feasible solution and the dual has no feasible solution, that is both the problems primal and dual have no feasible solution, in that case no solutions either of problem, that means बोथ जो प्रॉब्लम होगा उस दोनों का कोई सॉल्यूशन नहीं होगा यहाँ. ठीक है, so this is the conclusion and summary. Now let us comes to the most important theorems of duality. Okay, and based on this theorem there are questions from GATE 2021. Okay, so this is the most important theorem of duality, which is the complementary slackness theorem. Okay, so now complementary slackness theorem, there are 2 parts of this theorem. Okay, the first part is, if the strict inequality occurs in the ith constraint of the primal problem in its optimal form, then the ith variable of the dual is 0 in its optimal solution. That means what? What do you mean by this theorem? So if the strict inequality occurs in the ith constant of the primal problem in its optimal form, that means what? That means suppose the constant are ax less equal to b type. Okay, so if we put the optimal solution instead of ax, then if this inequality occurs only strict inequality, suppose x star is the optimal solution. Okay, so if a x star, this is less than b, strict inequality occurs after putting the values of the what optimal solution, then the ith variable of the dual is 0 in its optimal solution. Then क्या होगा, ये मतलब जिस कांस्टेंट में होगा, मतलब suppose this happens in case of third constant. Okay, so then in the dual the third variable is 0 in its optimal form. Okay, मतलब डुअल का जो ऑप्टिमल सॉल्यूशन होगा वहां पे थर्ड वेरिएबल 0 होगा, यही है इसका मीनिंग. ठीक है, लेट अस कम्स टू द एग्जांपल. सो the second part says that if the jth variable of the primal is non-zero in its optimal solution, then the jth constraint of the dual is a strict equality in the optimal form. That means what? Suppose you get a optimal solution x1, if there are 3, suppose what? If there are 3 decision variables in the primal problem and you get the solution, suppose x1 0 x3. Okay, so if x2 here is the 0, so and these 2 are the non-zero decision variables in case of primal. So if the jth variable of the primal is non-zero, that means if x1 and x3 are non-zero variable in primal of its optimal solution, then the jth constant in the dual is a strict equation. That means the first जो डुअल का क्या होगा, फर्स्ट जो इक्वेशन होगा या इनइक्वालिटी होगा कांस्टेंट होगा, एंड थर्ड जो कांस्टेंट होगा वो दोनों कांस्टेंट इक्वेशंस में कन्वर्ट हो जाएगा. ठीक है, तो इसका मीनिंग ये है. क्लियर? आई थिंक इट इज क्लियर. एंड इफ वी लेट अस कम्स टू एन एग्जांपल. So and alternative form, there are another alternative form, you can read it. For any pair of optimal solution x bar and u bar, u transpose bar, if of the primal and dual, that is this is the solution of the primal and this is the solution of the dual, then first part is the product of the jth variable of the primal and the jth surplus variable of the dual is 0. Okay, for j equal to 1 to n. And second one is the product of the ith variable of the dual and the ith slack variable. Okay, of the primal is 0. Okay, so these are another form or alternative form you can say. And there is an important remark, which is the slack variable gives the information about the dual. That is why the theorem is called complementary slackness theorem. Okay, so this is the case remark. Now let us come to the example. Okay, so this is a famous example, and the example is comes in GATE 2021. Okay, so this is very important. That is, this question is based on what? Based on the complementary slackness theorem. Okay, so see the problem. Suppose x 11/3 2/3 0 be an optimal solution. I say that this problem is already solved, already have the solution in our in my YouTube channel. Okay, you just get the LPP solution of 2021, the LPP solution of GATE 2021, and most of the questions of 2022 of LPP section are already solved in the channels. Okay, so you go to the GATE mathematics playlist, and I think you can get GATE mathematics playlist section, and you will get the the solutions of all the questions of 2021 and questions of 2022. Okay, so be an optimal solution of the following LPPP. Maxima is 4x1 plus x2 minus 3x3, and these are the inequalities are constant. x1 x2 x3 are 0 of real numbers. If y equal to pqr is an optimal solution of the dual, then p plus q plus r is equal to what? So this is the question. See, first, given that this is the optimal solution. Okay, this is the optimal solution of the primal LPP. Okay, that is it is given that in case of primal problem strict, if now we put this solution to the primal primal constant. Okay, and find in which constant gives, and that is in which constant it occurs or it gives the strictly inequality sign. Okay, so there are a and b presence in here, and a and b are real number. Okay, so we put the solution, optimal solution 11/3 2/3 and 0 in this set of constant. Okay, so this is the optimal solution of the primal LPP, and if we put the values, this is 10, this is 3, and this is 28/3, and see here, that is this is given 10. Okay, this is given 10, this is given 3, and this is given 11. Therefore, in first two cases, these two are equal. Okay, therefore we don't need these two. Okay, and the third one is strictly less than. Therefore, here I write that it holds the strict inequality in the third constant. Okay, so weak duality theorem says that, what says that in the first part of the weak duality theorem, if the strict inequality occurs of the on the optimal solution of the primal LPP, then what? Then the corresponding dual variable is 0. That means what? That means the third, this is occurs in the third constant. Therefore, the third dual variable, that is y3. I write here the dual variables. I first write the dual. Let us come to that point. So y3 is 0 in its optimal form. Okay, and it is given that since pqr is an optimal solution of the dual, therefore r equal to the third variable, which is equal to 0 clearly. Okay, so we get r equal to 0, and we have to find the sum p plus q plus r. Now from this question, we first write the dual, then we write the dual. So here we write the dual. This is maximize, therefore minimize, ye hoga minimize 10 y1 plus 3 y2 plus 11 y3. Okay, so this is the minimize optimization function, and the inequalities are, or the constant are here, the constant are less equal to type, therefore here it is greater equal to type. There is no confusion. Okay, so you can write the dual clearly. Okay, so this is the dual of the given primal LPP. Now we put the values. What now? Since x1 and x2 are the non-zero, then first and third constant in the dual must be equation in its optimal form. Okay, so this is the second case of the weak complementary slackness property. It says that if the primal variable, the decision variables in the primal problem in its optimal form are non-zero, and see here the values of x1 x2 x3 are given what? The values of x1 x2 x3 are given that this is, just a minute, So here it is given that 11 by 3, 2 by 3, sorry 4 by 3, I think 4 by 3 or 2 by 3, 11 by 3, 2 by 3. Okay, so 11 by 3, 2 by 3 and 0, that is these two optimal solutions are non-zero corresponding to x1 and x2. Okay, so since these are non-zero in the optimal form, therefore first and second constant in the dual must be equation. Okay, so and the duality in its equation in its optimal form, and optimal solution is given that p q r. Okay, and r equal to 0 you already get, therefore we put these p q r values to the dual problem. Okay, so this is the dual, so we write 2p plus q plus 2r, this is equal to 4, and 2p minus q plus 3 into r, this is equal to 0, and r equal to 0, therefore this part goes cancelled. Okay, so this is equal to just here 2p plus q plus 2 into 0 equal to 4, and 4p minus q plus 3 into 0 equal to 0, since the r value is 0 we already get. So this is two equation and two unknown, we can easily solve this, and after solution of this two equation two unknown, we get p equal to 5 by 6 and q equal to 14 by 6. Therefore p plus q plus r equal to 5 by 6 plus 14 by 6, which is equal to 19 by 6, which is approximately equal to 3.16. so this is the answer. This is very important problem. Okay, which is comes in GATE 2021. Okay, so this is a very important example of based on complementary slackness theorem. Okay, so let us comes to another example, and this is simple example for the dual problem, and after doing this problem here I end the duality. Okay, so then we after duality we start I think transportation problem. Okay, so this is the problem. The problem is maximize z equal to this one subject to this here inequalities. Prove that the question says that okay its dual has no feasible solution. Comment on the nature of the optimal solution. I take this problem because this is an different types of problem. Okay, so this is the problem, and the given LPP can be written as maximize z equal to 3x1 plus 4x2, and we all write the first we write it in its canonical form. Okay, and the canonical form is maximization and less equal to for this case. Okay, so we write here less equal to type inequalities by multiplying this constant by -1. Okay, we convert it to the canonical form, that is maximization problem. Considering, and since these three are less equal to, therefore we have to choose the slack variable. Okay, first we write the dual of this LPP. Okay, this is the LPP, and we write the dual of this LPP. Considering u1 u2 u3 are the dual variables, the following give the dual of the given problem can be stated as minimize w equal to this one u1 minus 4 u2 plus u3, and subject to the constant u1 minus u2 plus u3 equal to 0, and minus u1 minus u2 minus 3 u3, this is equal to 0. Okay, this is greater equal to 4 and greater equal to 3. Okay, so and u1 u2 u3 are get 0. So this is the dual of the given primal problem. Now since here two constant are greater equal to type, therefore we introduce here the surplus variable. So introducing surplus variable u4 greater than 0, we are now solve the dual. Okay, and u5 greater than 0, and since we take the artificial surplus variable, then we have to introduce here also the artificial variable, because this surplus variable cannot form the basis. Therefore to form the basis we have to add the artificial variables also. So the artificial variables u6 greater equal to 0 and u7 greater equal to 0, we write the dual of the problem in the standard form as. Okay, so maximize w equal to this, and here we take the cost minus m, which is a big positive number, m is a big positive number, and we take the cost corresponding to the artificial variable with a big negative number, that is minus. Okay, and minus u7, and this is also you know that which is the big M method of simplex algorithm. Okay, so subject to this one we write this type of inequalities. Then where if in m is sufficiently large positive number, okay, then choosing the, since u6 and u7 form the basis, therefore we choose the initial basic feasible solution is 0 0 0 0 0 3 and 4 corresponding to u6 and u7. Okay, now we write the table first. So this is the table. Okay, you all know that the which are the positions of the components and the components of the this table. Okay, so I don't go to the table. Now I just go to Zj minus Cj term. Okay, so Zj minus Cj is 1, 2m minus 4, 2m plus 3, m 0 0. Okay, see here, see that since all Zj minus Cj greater than 0 in the optimality condition, okay, so optimality condition has been satisfied, but the artificial vectors a6 and a7 are present in the basis and their corresponding artificial variable u6 and u7 are present in the positive level. Okay, see here u6 and u7 presents with a positive value, that is it says that positive level. Okay, and we see if these two are present in the basis with positive level, then we can't get the solution. Okay, because our solution is the decision vectors a1, a2 and a3, sorry, u1, u2 and u3. Okay, but there are no such vectors present in the basis. Okay, so there is no feasible solution of the dual problem. Okay, hence the primal problem has either no feasible solution or the primal problem has is unbounded. Okay, so this is the conclusion which are already we discussed above. Okay, so now if we plot the graph of this function, then we see that this is the primal graph of the primal problem. Graph of the primal problem is what? X1 minus x2 less equal to 1. So the equality is x1 minus x2, this is equal to 1, and then what? Minus x1 minus x2 equal to 4. So x1 plus x2 is equal to 4, and the next one is what? X1 minus 3x2 equal to 3. So x1 minus 3x2 this is equal to 3. Okay, so these are the three equations corresponding to the primal inequality or primal constant. Okay, constant of the primal problem. So x1 minus x2 equal to 1, I think 1 and minus 1, this one. Okay, so B and H, so this is the x1 minus x2 line. Okay, and x1 plus x2 equal to 1, I think equal to 4. Okay, so this is the line x1 plus x2 equal to 4. Okay, and the next one is this x1 minus 3x2 equal to 3. This is the line x1 minus 3x2 is equal to 3. Okay, now if we see that the graphical, by the graphical method, and this is the region solution region. Okay, so by the graphical method, see that the whether the primal LPP has any feasible solution, and this is unbounded solution. From the graph we see that the shaded portion of the feasible region of the primal LPP, this is the feasible region, shaded region, and this is unbounded. Okay, so hence the primal objective function is unbounded. Okay, so this is the conclusion which the problem which we have taken. Okay, above. So this is the conclusion, and I think this is a different type of problem, you can see it. Okay, so this is the content for this video. I'll share the content in the Telegram group. Okay, Telegram channel. The learning field. You can join the Telegram channel of the learning field. I will share the PDF, and sorry for that one the previous content. तो LPP का जो फर्स्ट 3 लेक्चर था एंड LPP का जो लास्ट लेक्चर था, आई थिंक जो 8th लेक्चर था LPP का, वो मेरा टेक्निकली इशू की वजह से वो नोट्स मेरा डिलीट हो गया यहाँ से. ठीक है, तो सॉरी फॉर दैट, आई कैन नॉट प्रोवाइड द PDF ऑफ द lecture 8 and lecture 1 to 3. Okay, so sorry for that. So if the content is helpful, then please give a like to this video, share with your friends, and subscribe the channel. Okay, because to make one video, it is very hard work. Okay, and it is very lengthy process to make one video and then upload. I just say that another video said in the another video. Okay, the video which I already uploaded. Okay, so please like, comment, share, and subscribe. Okay, thank you. See you again in the next video.